Welcome to GK's Tech Solution, and this video I am going to discuss about electronically controlled marine engine MEB 9.3 model, and this is also called .3 engine developed version of MEB engines, and this is similar to MEC engine except the exhaust valve is controlled by camshaft and with the timing unit, and this is the contents of this video. These chapters we are going to discuss detailedly in one by one. Next is engine type designation. This slide I am giving for your reference, and the details is given about the letters in the model designation, and ours is MEB, that is exhaust valve controlled by camshaft. Next is engine control system. This slide shows the actual setup of MEB engines, and each unit is controlled by cylinder control unit, which will give the exact timing of fuel injection and exhaust valve operations, which will get the feedback from the engine RPM through crank angle encoder, and also the actual position of the crank, so that can easily achieve the timing of fuel injections. And all the cylinder control unit is connected through network to the main operating panel, through which human can enter the reading and can read the actual values, and easily can troubleshoot also we can do with that. And there is a two MOP main operating panels are there for redundancy, and MOP B is actually having the troubleshooting facility, through that we can troubleshoot online only, and PME computer, engine diagram system, also there through hub it is connected with MOP, so that we can performance we can check, and auto tuning also we can do it. Auto tuning means we can all the units getting balanced with automatically, and this we will discuss about later detailedly. And one more unit is there, EICU, which is actually getting interface with the telegraph units from the bridge and ECR panel, and also that the EICU controls the HPS pumps. High pressure pump is required for MEB engine. For controlling that also it is done by EICU, and engine side control also there. It is all communicated with all cylinder control unit. In emergency we can operate from this engine control side, and this cylinder control unit also controls the alpha lubricator to the units for cylinder lubrication, and all cylinder pressures are measured with sensors fed to MOP-B through data acquisition unit, and from the MOP you can compare and check the pressures and tidings of the fuel injections and pressures values, and then this data will goes to PMA computer through hub. This is the setup, and portable measuring instrument also can be used through PMI data acquisition unit for calibration purpose, and this is the setup, and we will discuss about one by one section detailedly now. Next is high pressure system. Actually MEB engine concept is use of mechanical hydraulic system for actuation of fuel injection pumps, which are electronically controlled by a computer based control system, and for that main system lube oil is used as a hydraulic medium. This oil is further fine filtered by the auto filter unit, and then pressurized by two electrically driven pumps to 300 bar, and for this accumulator block also we are using to get the stable oil supply to the hydraulic control units where the fuel pumps, injection pumps are fitted, and this is the setup. And after hydraulic control unit, the oil is returned back to the pump suction. and this pressure is controlled by proportional controlled pressure regulator and by EICU, as already we saw that, and this is the setup. Next is crank angle encoder, which is very important for electronic engines, which will give the actual RPM and actual crank angle position to achieve the proper timing of fuel injection and exhaust valve operation, cylinder lubrication, etc. And this will achieved by this encoders, and one encoder as a reference encoder we are going to use later, and this encoder is fitted behind the flywheel, and this will sense the position of the flywheel by sensing the semicircular ring. It is fitted behind the flywheel. You can see that blue color ring, and this ring is fitted 90-degree offset from number 1 unit TDC. This we will discuss about later. And the next setup is that hydraulic control unit for 2 cylinders, 1 hydraulic control unit which will accommodate 2 fuel pumps and the electronic fuel injection valves plus cylinder lubrication. This is the high pressure pumps fitted, and all the high pressure pipes will be fitted inside the crankcase for safety reasons, so nothing high pressure pipe will be outside. That is very important, and this is the accumulator for giving the stable hydraulic supply. And this is another 2 encoders. This is the main encoders. It's fitted forward of the engine. There is 2 they are given for redundancy, and the behind one is that first one is that encoder A, and second one, outer one, is called as encoder B, and encoder A is exactly fitted on number 1 TDC. The reference, it will take the reference from number 1 TDC, and second one 45-degree offset from the number 1 TDC. They fitted in that way, and in few minutes I will explain you why this offset is required, and this is the setup they are given. And next, from this encoder the signals will go to this amplifiers, this encoder amplifier. From here, this is the actual setup, actual photo of the main engine, and now I will tell you how the encoder is working. It is just like a disc. It is rotating along with the shaft, and this setup is having infrared lights in one side, and the disc is having windows, having a transparent windows. Through that the lights are passing, and then the sensors is receiving the lights, and this will give the signal to the amplifiers. So from that you can measure the RPM and crank angle also, and we will discuss about this detailedly, how we are achieving the RPM plus crank angle with the sensor. And this is the setup, and with this small animation I will explain the working principle of these 3 encoder together. And there are 2 encoder in the forward shaft, you can see, and blue one is that encoder A, that is a main encoder. It fitted exactly with the number 1 TDC, and this is the encoder B. It is 45-degree offset from the number 1 TDC they fitted, and the third one is that flywheel encoder. It is you can see the marker that of semicircular ring fitted 90-degree offset. Now you can see that on rotation how the thing is going on, and it is having so many sensors, not only marker sensor, it is having a quadrature sensor also. And in few seconds we will discuss about these sensors, what is the difference and why it is required this many sensors for one encoder. And you can see that one encoder, it is having 4 sensors. So what is the purpose of 4 sensors? In a few minutes we will discuss about that. And now one by one we will go with this small animations. And now you can see that we have this many sensors. That main sensor, big one, is that marker sensors, and 2 marker sensor in one encoder, which will be 90 degree offset, and small sensor together fitted, it is called quadrature sensor, that is for calculating the RPM as well as the direction of the shaft. And this is the setup. For easy understanding, I removed the crankshaft and then I am showing what we are doing. And now what I am going to do, all the sensors markers I am going to turn in one direction, bring it in one position like this, so that easy for us to understand the position, what is happening, and which sensor is giving in signal, and with that what we can understand. See, this is the normal drawing normally available in the manual, and you can see that 45 degree offset the encoder B is set it. Now I will explain about this incremental encoder. This is the basic type, which is having only one sensor on the wheel, and with that sensor we are getting the signal like a graph as shown in the down below. And with this graph we can measure the RPM, only RPM, not the direction of the wheel as well as the crank angle position. So with that we can achieve this much only. For getting the direction, we need the next encoder called quadrature encoder, which is having two sensors together like as shown in the figure. And because of these two sensors together, we are getting two graphs signal outputs like below, and you can see that number 1 A sensor is leading than number 2 sensor. So with which is leading, according to that we can find the rotation of the wheel. That is the idea of this sensor. And with the timing also we can measure how much angle it is rotated. That is also is possible with this quadrature sensor. And the next one is that absolute encoder, which will give the exact crank angle also. And here the marker sensor, it is additional sensor fitted with the marker ring, circular ring on number 1 TDC. So whenever the marker ring crossed the marker sensor, it will give the starting point of the crank. From that we can get all the angles by the measurement as shown in the slide. From this we are achieving the crank angle position also. Next we will discuss about why the marker ring they given 180 degree and also 45 degree 90 degree offset from number 1 TDC. The reason behind is that when the switch on the power after power shutdown or anything, then the system should understand which angle position currently the engine is there to achieve the starting position for the electronically system. So for achieving that we are giving this 45 degree. This animation will show you in each position the status of all 4 sensors in the tabular column. With this we can achieve which 45 degree actually the engine is now it is there, so that unit starting valve will start for initial movement. If one revolution we achieved, then all system will get resetted with that actual position. So after that the computer will calculated the correct angle, and all the system will continue to run. In this system, instead of sensor MSA in the encoder A, there are a flywheel sensor used as a reference sensor. The reason behind this, there is a chance of error in encoder A and encoder B sensors getting slipped from the shaft. So but flywheel sensor is a fixed one, will not get error anytime. So we are using this sensor as a reference sensor to calibrate the other sensors. This is the reason they given the flywheel sensor. I hope you understand all the features about this encoder, how it is working, and how much useful for finding exact position. Next is that fuel oil pressure booster. which is actually fitted on hydraulic cylinder unit. From the LV valve, the hydraulic cylinder unit getting a high pressure oil flow. This oil flow pushes the hydraulic piston up, and this hydraulic piston will pushes the fuel oil plunger, which is in the top upper position as shown in the figure, and one umbrella is given for protection of spillage, any mixing of fuel oil in the hydraulic system. And the fuel oil will go in through this non-return valve, and it by the injection happen, then the fuel oil will inject through the high pressure pipe and fuel valves. After injection over, the piston will return back, hydraulic plunger will return back, so that that is happened by the fuel oil pressure is pushing down. This there is no spring in that, and hydraulic accumulator fitted to get stable hydraulic supply all the time. Next is that electronic fuel injection valve named as LV or FIVA valve. It is a proportional control valve, solenoid valve, which act as a pilot valve for the main spool valve, and this is will controlled by the PCB, which is a computer processor, which will activate the voice control drive, which will move the spool of the pilot valve, and end of the pilot valve having the self-centering spring, which fails safe whenever the power switched off, then this will become in the center. And this pilot valve will fitted on the main spool valve, which is actually allow the high pressure oil to the fuel oil pressure booster. And this is the actual setup. Pilot valve is fitted on the main spool valve, and in the end of the main spool valve you can see that LVDT sensor is there for finding the position of the spool, actual position of the spool, and it is the feedback, it is again passed to the LV valve PCB, which it will compare, and if any error is there, then it will cut off the unit. And now I will show you that the mechanism with a small animation, how the spool valves are working. And now in this picture you can see that LV valve is operated by voice coil drive. Through that we can move the spool, pilot spool, and the pilot spool will allow the high pressure oil to the main spool, and main spool will move move up and down, so that we will get the passage of oil flow to the high pressure booster. And for a feedback sensor they give an LVDT sensor for the main spool, and FIVA valve also having a sensor is a pink color, you can see that one near the voice coil drive. And in few seconds I will explain how the voice coil drive is working. And this self-centering spring, it is for fail-safe. In any power failure happen, then the pilot valve spool will become in center position, and the main spool valve will be in the same position without moving. And now we will discuss about voice coil drive. This is the setup of voice coil drive, having a permanent strong magnets in the stationary inside the coil drive, and the coil is a movable coil. It's series for getting a more power, and the current controller will give the proportional current, so that with the depends on the current, that amount of the movement will be vary. That is achieved by the proportional controller of FIVA valve, and it's having a position sensor also, will give the feedback of how much the valve is moved. And this is the voice coil drive mechanism. And next one is that sensor, LVDT sensor, that is called linear voltage differential transformer. As the name itself, it is a transformer having a primary and secondary coil. Primary is given by the 24 volt supply, and secondary is seriously connected, but in reverse manner, like shown in the figure. When you are changing the spool, then the current it's passing through this transformer. You can see that how the voltage is varying in the meter. Accordingly we can get the position of the main spool. This is actually fitted on the main spool. to get the position. Next is that plunger position sensor. It's having inductive distance measuring sensor which will give the distance between the sensor and the taper portion, which will convert to the linear movement so that we can calculate the exact position of the plunger, which is normally fitted in fuel oil high pressure booster plunger. Next, we will discuss about how we are achieving variable compression pressure by adjusting the closing timing of exhaust valve through the timing unit. The timing unit piston is known as MEB piston, and from the spool valve through the passage B, the high pressure oil will pass below the MEB piston, which is will push the MEB piston up, so that some extra oil will pass through the high pressure side of the exhaust valve actuator. Which what actually is happening, this will happen only in the downward stroke, that is called closing of exhaust valve stroke. How they are achieving, they made a cut in the closing profile of the cam. You can see that is why this is called short cam. And opening time means the plunger upward direction there is no cut and the normal profile will be there, and only the downward stroke, that is the other side of the profile of the cam, having one small cut to achieve the early closing of the valve to get more compression pressure in low load. After achieving some load, 70%, about 70% of the load, the MEB piston will give excess oil to compensate this cut of the camshaft. That is called short cam or dot 3 cam used to mention, and by that way we are extending the timing of closing when more in higher load to achieve the variable compression pressure. And this closing also can be achieved by this LFI valve. With this small animation you can understand clearly how the thing is working. When it is coming down, the actuator is coming down, that time that MEB piston is going up. You can see that one, and this is the way they are achieving the variable compression pressure. And for this two pipeline, it is below the cam case coming from the hydraulic cylinder unit. You can see that green pipe and red color pipe, it is there. This is the new development in dot 3 engine, a 9.3 version of MEB engine, and the animation shows you the exact one, and pistons having a proximity sensor to get the feedback. If any failure in that, it will cut off that unit when engine is in operation above 70% load. So this is the full mechanism of exhaust valve, and here you can see that the difference between the normal cam and the new short cam, there is a cut in the right side which is happening in the lower stroke of the actuator, and this is the two pipes below the camshaft which is passing from HCU to the actuator. Next we will discuss about the alpha lubricator, which is similar in MC engines. It is also fitted in the same hydraulic control unit, activated by the same high pressure oil, and it is having a main piston having a multiple small pistons which will give the supply through the non-return valve to the respective keys on the cylinders. And this is the oil supply system having level sensors also there to give the alarm, and the piston movement, there is an inductive sensor to give the feedback to the controller. In any movement is not error in the movement, then it will raise the alarms, and it is having a non-return valves and spacer also to adjust the stroke length of the piston. And this solenoid is on-off solenoid, and one stroke there is a fixed amount of oil will pass through it, so that every revolution of the unit from the CCU, it will get frequency of the pulse, number of pulse. So according to the number of pulse, the quantity will vary with the load dependent or quality or whatever setting we are doing in the MOP. It will give the frequency of how many pulse has to give to this piston. Depends on the number of pulse, the number of stroke will happen and the quantity will vary. This is the way this alpha lubricator is working, and this is very similar to the alpha lubricator which normally used in MC engines. And in MC engines we are using a separate pump for making the high pressure oil, but here we are utilizing the same high pressure oil and from the HCU unit. And this is the small animation, you can easily understand. Next we will discuss about main operating panel. We have two main operating panel as a full redundancy, and one we called as MOPA and one we called as MOPB. And MOPB is the main operating panel which is having direct connection communication to PMI computer, that is a computer controlled surveillance computer. And also the MOPB is having a troubleshooting screen. Through that we can troubleshoot in any fault event or any problem occurs. And we will see one by one with the pages what are the things is available, what we can do, what settings we can change. Next, the alarm is the first menu. Under that sub menu, alarm list will show the alarm which is still activated, and next page will be the event log. Event log will show the what are the alarm previously occurred and rectified or resetted. And next one will be the manual cutout list. If anything manual cutout in the event of we know the fault, like a lubrication fail or some alarms, if we cut out, then that will show in the list. And next one is the channel list, and which channel, which system is connected, which sensor is connected, everything will show. And next one is that engine. Under that operation screen is there. Through this you can see that RPM which is Agada Rastin, and bridge control or ECR control also is showing here, and then RPM mode also showing, and then fuel index is showing here, and with the limiter which is limiting the fuel index. Sometimes is limited by scavenger pressure, low scavenger pressure or high torque, or your set point is limiting. That is also will be clearly it is showing here. And then we can see that lube oil pressure and scavenge pressure also is visible, and engine running, stopped, everything it is there. And the hydraulic pump is also showing whether it is running, how many pumps are running for hydraulic pressure system. So this all data is available in this operation menu, operation screen. Next one is that we will go to the process information. Under this process information we will get this data, hydraulic oil pressure, scavenge pressure, and which mode is running, how much load is there, fuel index, how much percentage fuel index is there, then that speed control, the limitation is showing, and propeller RPM, and how much speed is, fuel index is there achieved, and all it is showing. Then the process adjustment is here. In that first one is auto tuning. With that we can set the auto tuning, automatically balance the engines, and then it is the cylinder load details, and then cylinder, then next one is the cylinder pressure, and then next one is the fuel quality. Fuel quality also we can set that fuel quality with depends on the fuel you changed, and you can enter the calorific value and density, sulfur, everything here, so that it will be helpful for calculating the cylinder lubrication. And plus next one is the chief limit. The chief limit you can set it to 1 or 2%, to 111%, like that. it's a maximum stiff limit. Then this next one is that we show that hydraulic system, how many pumps are running with the pressure regulators, and bypass valve is there. If any leakage happen, then the bypass valve will open and reduce the leakages. And next one is that cylinder lubrication, the quantity of cylinder lubrication details. And next is the maintenance. Maintenance, the first one, system view. Through the system view, all the MPCs you can see, MOP and MPCs. This MPC we will discuss about later. And if you select one, like for example CCU1, you click that one, you can the CCU page, all the channel connectors page will open, and it will show all the connectors with the value which is getting from the connection sensors. So for example, I am pressing that channel 30, which is LFE supply set point, and through that we can see that connector wire also. If any wire is break also, we can easily find out from here. And this method easily we can do the troubleshoot also. And next one is that any invalidated input from the wrong sensor, damaged sensor, error in the sensors, it will be shown here. And then next one is the network status. We will show the network connection. If any disconnected wire is there, it will shown here with the red mark. And then next one is the function test. Through this we can test the encoders positions, and any error or slip is there in the encoders, like that we can do the test method here. And then next one is the troubleshooting, which is very important. With this, all HCU event you can store at any event by triggering, or if any alarm occurs also, it will automatically save one event here. With that event you can see in the computer, offline computer, we can analyze the fault with this graphs. We will explain later about this detailing. And next one is that troubleshooting screen, and that is next one is time setting inversion, and this only can be done with chief limit. Now we are in operator level, so we have to go to chief level by putting the password. And if you put the password, you can enter into the chief level. You can change the time settings if you required. Next one is the version is given, and this MOP only, all the MPC software is loaded. From here, if any MPC changed, it will get loaded there. Software will install, configured there. Next we will discuss about PMI auto tuning computer, and this is a separate computer which is connected to the MOP-B through the LAN hub, and it will take the data from MOP-B from the data acquisition unit through the data acquisition unit to the MOP-B, and then it will reach to this computer, and it will store here only, and all the things will get analysis here, all form of chart, and this one we can visualize from this computer. And in this same computer also having computer controlled surveillance software also, that is also will be connected with this same computer. And we will see one by one which is what is available in this computer. This is actually the pressure measurement software tool, and with that we can see that all the units pressures, cylinder pressure like compression pressure and peak pressure and indicative pressure, with the form of bar chart like this, pressure crank angle diagram, or pressure volume diagram, or all together along with all units, say in one revolution, so that we can compare with the other units with the graphical representations. And also we can save this one in the form of tabular column, and then we can review in later timings, and we can compare with the older set of records. That is also possible with this software. And the auto tuning is actually happen from this software only. This will give the feedback data to the MOP, and through the MOP-B, and then engine will get automatically auto-tuned. All the units get balanced by adjusting the timing of fuel injection and exhaust valve closing timings. And these also things is available here, and this is very easy understanding when you are operating directly on the computer. And next one, next one is that computer control surveillance, COCOS. This is also one good software. It is also stored in the same computer where PME auto tuning tool software is installed. With this we can get all the data in the tabular form like this. This report normally is easy for record keeping, and even all the data, online data, we can see like this. And with that, a lot of information you can arrange, and you can save also with that.